Hello, Debbie. Can you see and hear us okay? And JC?
I can see you really good.
All right. Could you share your all's computer or on the Crestron, the Podium PC? We don't have the computer in the room. If it's ready to share.
I can. I usually wait till he comes in here, but yeah, I can go ahead.
Either way, just so you know it's not shared, I wanted to go ahead and tell you.
Yeah, thank you.
Yeah, you can do it whenever you want to.
I got it.
Hey, where I thought we'd start tonight's right here. We are on 4, right? Seems like that's where we're at. And it's a regression problem, and it says, obviously on the survey, question 9 asks students, how many wrecks have you been in where you were the driver? And question 10 asks, how many speeding tickets have you received? Oh, well, seems like those should go hand in hand, doesn't it? We are interested in seeing whether we can use the number of speeding tickets to predict the number of wrecks a student has been in where they were the driver. Now here's the thing, you see that word predict? We always use the explanatory variable to predict the response, right? So we're trying to say the number of speeding tickets should be your explanatory variable, your x, and the number of wrecks should be your response variable or your y. Because look, this is a regression problem, so you know I'm going to make a scatter plot. There's going to be a least squares regression line and the whole spiel. It says create an appropriate graph to display the relationship between tickets and wrecks. And somebody remind me what I just said there. So I'm looking for graph, scatter plot. We just want a simple one, right? We don't want anything fancy here. And look, we're looking at speed and wrecks, yes? And we were looking to see if the number of speeding tickets could help predict the number of wrecks, right? Did I got that right? It makes a difference. So we want to use the number of speeding tickets to predict the number of wrecks. The number of speeding tickets should be your x or your explanatory variable. The wrecks should be your y, right? So get them in the right order for me so I don't have to count that wrong. Because if not, you know, you'll have the wrong one on the x and the wrong one on the y. Okay? So I'm going to click OK. And I looked at this like a week or so ago. That's about all I can give you, though. Right? That's not what I would consider to be a good-looking picture. Let's make sure we got it right. Use the number of speeding tickets, explanatory variable, predict the number of wrecks. Speed tickets should be on the... Is that what? Oh, well, okay. The other one don't look any better. Thank you. Scatter plot, simple. I got Rex's right? So it should be always tickets, not the speed you drove. Yes? Better? It'll look better. Right, so then the number of tickets for speeding should be on the X, the number of wrecks should be on the Y. There's my scatter plot, right? That's what you're going to copy and paste over here. And then based off what we're looking at here, does the plot show a positive association, a negative association, or no association between the variables? Explain what this means. All right, if you force me, I'll say something maybe shows a little bit of a positive association, right? In other words, as the number of tickets for speeding increases, it looks like we might increase the number of wrecks that this person was involved with, right? And things aren't good, but it does look like I'm a little bit going from lower left to upper right, okay? So I do see some kind of positive association. What does that mean? Well, as the number of tickets for speeding increase, the number of wrecks that the student was the driver increased. Okay? It says explain, which I did. Describe the form of the relationship between tickets and wrecks. All right, you know me and you, we always look at these and we always compare them to linear. So I'm thinking, I'm going to give you like slightly linear. I mean, this is not going to be strong by anybody's imagination. I'm going to give you slightly linear. And, if you force me, I'll give you a slightly linear. It's not what I would call really good-looking picture here, or a really good-looking scatter plot. Report the value of correlation between this pair of variables. Here will be the telltale sign to see if we actually get something that is stat, basic statistics, correlation, what was it? Recs and tickets. I'm going to get rid of that display p-value, I always do. How strong are things? Well, at least it's positive, so I did say that I saw a positive association, right? But at 0.411, is that very strong? Because that's what they're getting ready to ask me. Right? They're getting ready to ask me here, okay, report the value of that. Based on the information displayed in the graph and the correlation just reported, how would you describe the strength of the association? I'm going to give you like moderate, right? It's moderately weak, positive linear. 0.411 is not very good, right? Hell, we're less than our 0.5. So the best you're going to come in, you see something that's moderately positive linear, okay? It says, use Minitab to obtain the equation for the least squares regression line, copy and paste. I'm going to do it like this for you because this is the way I showed you before. I want to go to stats, regression, fitted line plot. I want everything at one time here. I want the line on there, I want the equation of the line, I want the scatter plot. Remember my response is the number of recs and the predictor, the x is the number of tickets. So it looks like my regression line is the number of recs is equal to 0.4075 plus 0.2466 tickets, right? That's what I expect you to copy and paste. I'll see that you got the regression line there. It says, interpret the value of the slope in the least squares regression equation you found in part F. Let me ask you this. Which one of those numbers is the slope? It's always the one that's on your explanatory variable, right? On your x. The slope there is plus 0.2466. What's the interpretation of the slope? If you increase your explanatory variable by 1 unit, the value of your response variable will increase by the slope of its positive. I'm not going to do any better than that. You've got to put the words of the problem in there, right? Okay? Use the regression equation to predict the number of recs for a student that has 3 speeding tickets. How do you do that? You plug in for 3, pull your calculator out, tell me the number of recs. Okay? And then finally, how well does the regression equation fit the data? Explain, justify your answer with appropriate plots and summary statistics. You see the little r squared there being 16.9%? How well does the line fit the data? 16.9% of the variation you're seeing in the number of recs is explained by the linear relationship with number of speeding tickets. That means that 83.1% of the variation is coming about the spread of the points about the line. Let me ask you this. In part H, you use the regression equation to predict the number of recs for somebody who has 3 speeding tickets. How do you feel about that prediction? You feel good or not? I'm not going to give you the answer to these things, right? I'm just pointing it out. When you start talking about how well things fit, you want to talk to me about that 16.9%. That's one way to do it. I guess another way to do it is you can give me the residual plot. Let's go right back there. Stat, regression, fitted line, all that stays the same. Graphs, I want the residuals versus your explanatory variable. Oh, you can give me that plot too. How's it look? I got all kinds of spread going on. Actually, nothing looks good with this problem to me. The R squared's not good. I don't trust your prediction. The original scatter plot didn't look good. Hell, the residual plot doesn't look good to me. That's just what I'm saying. You fill in the pieces. Now remember, you do have old project solutions to look at, right? And every one of the ones I gave you has a number 4, and it's always a regression problem. Go and look and see how they said, how did they interpret the slope in their problem? How did they tell you about how well does the regression equation fit the data? You better be mentioning R squared being 16.9% and tell me what you think about that 16.9%. Okay? That's the deal. On Thursday?
5.
Oh, 2 two-way table. We'll come back and talk about 5 on Thursday. So where me and you left off last Thursday is we were talking about, I'm going to give it to you like this. That's the null hypothesis. Remember, every test of significance we do, there are 2 hypotheses to be stated. There's the null. There is H sub A, which is the alternative. Now, I'm going to give you that little list of things I gave last week, but all I'm going to do is say them out loud. The null is the one of no effect, no difference, the status quo, what you're used to seeing. It's a statement that mu is equal to some value. It's the statement we assume to be true to get ourselves started in the test of significance. It is the statement that we are seeking evidence against. That's about all the things I can think about with the null, right? The alternative is, that's the one you're seeking evidence for. There are 3 different alternatives. There's like one-sided to the high side, one-sided to the low side, or two-sided, not equal. See, when I think about the alternative, I think about these little symbols. And when I think about the null, I think about that symbol. Right? The null is a statement that mu is equal to something. The alternative is a statement that mu is less than the number, greater than the number, not equal to, depending on what the problem is asking for. All right? Now, what I want to do is this. As long as we are making statements or claims about a population mean mu, my template looks like this. In other words, if we're making claims about a population mean mu being something this or something that, or seeking evidence about mu this, that's your template. I don't know what value will go in here. I'm going to put a little question mark because that's going to come out of the problem, as I'm going to show you here in a moment. And then whatever that number is, that number goes there. If that number is 20, 30, minus 72, whatever the hell it is, it goes there. And then what goes between here? How do I know if it's one-sided to the high side, one-sided to the low, or different or not equal to? The problem will tell me that. The way the problem is worded will tell me which one to pick here. Now, what I want to do is this. I want to look at this 17.5 on page 396. Before we calculate anything, I just want to know if I can pull the information out of the problem here. And so, 17.5 says the examinations in a large multi-section statistics class are scaled after grading so that the mean score is 75. The professor thinks the students in the 8 a.m. class have trouble paying attention because they are sleepy and suspects that these students have a lower mean score than the class as a whole. The students in the 8 a.m. class this semester can be considered a sample from the population of all students in the course. So the professor compares their mean score, their X bar, with 75. It says state the null and alternative hypothesis. My template is now, the way I usually do it is, I know I'm going to assume the null is true and all that, but usually the problem is talking to me about the alternative, right? What we're looking for evidence for. And you'll notice here it says, the professor thinks the students in the 8 a.m. class have trouble paying attention because they're sleepy, and suspects that these students have a lower mean score than the class as a whole. The class as a whole has an average of 75, right? He suspects that that group has a mean less than 75. If 75 goes there, 75 goes there. Now, notice this is a one-sided test. It's one-sided to the low side, however you want to think about that. You're only looking one direction, and what gave me the symbol? It was the way the problem was worded. And then if I look at 17.6, it says, the average income of American women who work full-time and have only a high school degree is $35,713. You wonder whether the mean income of female graduates from your high school who work full-time but have only a high school degree is different from the national average. Now you notice I emphasize the words that are important to you because I'm the guy reading it. Different than the national average. You obtain income information from an SRS of 62 female graduates who work full-time and have only a high school degree and find that X bar is 35,053. What are your null and alternative hypotheses? The null is equals. The alternative is mu, I don't know. Now, where's the numbers come from and my symbols come from? You wonder whether the mean income of female graduates from your high school who work full-time but only have a high school degree is different from the national average. What's different mean? You didn't pick a side. Different means not equal to, right? Different from the national average. And then which one of these numbers is the national average? That's that 35,713. That 35,713 goes there. The other one's an X bar, right? That's about samples. That has nothing to do with my statements about you. And then I got to do one more. Notice, this is a two-sided alternative. Both sides. We'll take either side. And then 17.7. In planning a study on the number of days in the last 30 that high school students texted while driving sometime during a day, a researcher states hypotheses. Here's what the researcher states. And the alternative was greater than 15. And then it says, what's wrong with this? What's wrong with that? That person, this can't be a very good researcher. They're stating their hypotheses in terms of X bar. No. The point is, the hypotheses, the null and the alternative, are always stated in terms of a, I'm going to give it to you in general. They're always stated in terms of population parameter, and in this chapter they're stated in terms of mean. They're not stated in terms of X bar. Right? X bar is where the evidence comes from. How's that? So you'll notice I've got all my little symbols. We've got problems. We've got them all in there. Not equals, different. Less than means it scored less than 75. I just wanted to do a couple of these to show you. Look, I know the one I did last Thursday, mu was 0 versus mu was greater than 0. I don't want you to think it's always 0. The numbers and the symbol in the alternative comes from the question. All right? Now, that's the first step in doing a test of significance, being able to state the hypothesis. It's just reading the question and getting the information out there is what to deal with. Now, I'd like to have a little chat with you about something called a test statistic. And something called a p-value. Okay? So I'm going to point you to this. And I'm on page 396 here, and there's a box there. All right? I'm not going to write this down because they're kind of long definitions here of what your test statistic is and what a p-value is. But here's the deal. It says, test statistic and p-value. It says a test statistic calculated from sample data measures how far the data diverge from what we expect if the null hypothesis is true. In other words, I'm going to do this part here. Everything comes to us in terms of an X bar here. Okay? Now, if you want me to be real picky here, a test statistic to me is nothing more than a Z-score. All right? A z-score tells you how many standard deviations away from the mean your observation is. In this case, it's going to tell you how many standard deviations away from the mean x bar is, right, that came from the data. That sample mean your statistic. So a test statistic is a z-score, and the way we want to think about it is, look, what the hell does a z-score measure? It measures how far an observation is from the mean, whichever direction, depending on the sign, correct? If the null hypothesis is true. The way I think about it is, your test statistic, your z-score, measures how far your x bar is out the table. The larger your test statistic, whether it's negative or positive, I don't care about the negative or positive, I care about how large the number is. To me, a z-score of negative 3.47, that's large. Because that means your x bar is 3.4 standard deviations to the left or smaller to the mean out that table. I also think about 4.72 as a large z-score, right? Because your 4.72 standard deviations greater than the mean. The point is this. Large values of the test statistic. Positive or negative just tells me the direction. Okay? Or show that the data, and when I think of data, I'm thinking of my x bar, is not consistent with H naught being true. Right? In other words, here's what I'm telling you in plain English. You give me an x bar, and we calculate this z-score, this test statistic, and it's really far out the table. One way or the other, right? So I got a large value. Whether it's negative or positive, I got a large value. Minus 3.42, 3.68, whatever it is, it means your x bar is a long way away from the center, right? Well, the null hypothesis is telling you where this thing is centered. And so when I say it's not consistent with H not being true, it means, okay, you're telling me you're centered here, right? That's what the null hypothesis says. And all of a sudden, you give me an x bar that's got a large test statistic, a large z-score, you're really far out the table. Did you actually get that x bar? Yes, you did. So what's wrong? Well, it's so far out the tail, you can't be centered here, you must be centered somewhere over here. In other words, you've got evidence in favor of the alternative, right? See that last line? Show that the data, x bar, is not consistent with H not being true. Another way to say this is, you have evidence against the null hypothesis being true and in favor of the alternative being true. I'll give it to you like that. So when I see a large test statistic, oh, the data is trying to show you H naught is, we're not consistent with that. You have evidence for the alternative and against That's what it means for the x bar, the data, the z-score, the test statistic not being consistent with H not being true. Folks, the simplest way I can tell you is you don't believe the null hypothesis at this point, you actually believe the alternative. Right? You've got evidence for the alternative and against the null hypothesis. Now, you see how it says large values? What happens if I get a small value of my test statistic? In other words, let's say I calculate my z-score and I get, my z-score is 0.42. So your x bar is 0.42 standard deviations greater than the mean. Or you get let's say a negative 7.2, which means your x bar is 0.72 standard deviations to the left of the mean. What does that mean? That means the data is consistent with H not being true. You failed to find evidence for the alternative and against the null. When you have a small test statistic, you cannot tell me the null hypothesis is true. That's not the way this is played. You give me a large test statistic, and my hands move the same way every time. Large test statistic means you're out here. You don't believe the null, you believe the alternative. A small test statistic's in here, The data is consistent with the null hypothesis being true. I'm talking to you all about this just with a z-score. Okay? Now, everybody wants to take it one step further other than just looking at a test statistic and the z-score. They want to talk about a p-value. Well, a p-value is a probability, all right? So, you know, a lot of times I write p-value. Sometimes I'll just write capital P. And I would like to look at the definition here. It says the probability computed assuming that H naught is true. All right, so here we assume H naught is true. Folks, everything we do, we assume that the null hypothesis is true, that mu is equal to some value. It tells us where our sampling distribution is centered. All right? Now, it says that the test statistic would take a value as extreme or more extreme than actually observed is called the p-value test. Now, what does it mean to be as extreme or more extreme than what's actually observed? I'm looking at some normal curve. What area am I looking at? I can't say, look, they gave me both of them. You know, if I'm looking this way, right, on the high side, it would be as large or larger, yes? If I'm looking on the low side, it would be as small or smaller. It's the area in the table. It's telling you the probability that you would get the value as extreme or more extreme than what came from the data, your X bar and that z-score. Here's the point about this. Small values, small p-values, small probabilities are evidence against H naught in favor of the alternative. Now, I'm going to spend the next 3 weeks with this thought in your head. Large values of your test statistic, large values of your z-score will produce small p-values. They're the opposite of each other. Small values of your test statistic will produce large p-values. Think about it. The larger your test statistic, the further out the tail you are. The further out the tail you are, the less area that's in the tail, yes? So a large test statistic will produce a small p-value. I'm telling you the same thing here, right? Small p-values are evidence against H naught in favor of the alternative. Large values of the test statistic are evidence for the alternative and against the null. They go together. Large values of your test statistic and small p-values, small values of your test statistic and large p-values go together. Now, if small p-values are evidence against the null in favor of the alternative, what do large p-values mean? What's the flip side to this? Well, hell, the best I can make it for you is, are not evidence against H naught in favor of the alternative. The data are consistent with H naught being true to get a large p-value. Now, here's what I would like to do. Okay? I'd like to find us a problem here and go from start to finish. Okay? And I'm thinking we should look at how about on page 404, okay? I want to go to page 404, and I want to get things started a little bit here for you, all right? If I go to 404, and we look at 1715, all right? I'm going to need help from somebody here, because I'm going to need somebody to calculate my X bar, because they're giving me the data and all that kind of stuff. It says, people tend to be more generous after receiving good news. Are they less generous after receiving bad news? The average tip left by adult Americans is 20%. Give 20 patrons of a restaurant a message on their bill warning that tomorrow's weather will be bad and record their percentage tip they leave. Here are the tips as a percentage of the total bill. Look, somebody just took a sample size 20. I'm on here and somebody needs to average these up and they need to give me my X bar. Okay? It says, suppose that the percentage tips are normal with a standard deviation of sigma equal to 2. Remember my simple condition? Well, they gave me this. They gave me that. I still don't see simple random sample yet. There's nowhere there I'm seeing that somebody gave me a random sample, they just gave me 20. Okay? So what'd you get for X bar here? Anybody? No shit. Huh. That ain't no problem. That's 1715, right? So if I go here and find chapter 17, where the hell I put these? Yeah, I can see my head exploding. So there's those 20 tips, right? So I would like to find the X bar, basic statistics, percent, X bar. X bar, the mean is 18.19. Oh, there we go. My X bar is 18.19. All right. If you were doing this, you'd have had to add a 20 up and divide by 20. You would have got 18.19. It says, is there good evidence? So I'm going to highlight that word. Evidence means test of significance. Normally the way everything's set up is this good evidence, and whatever comes after that should be your alternative hypotheses. It says, is there good evidence that the mean percentage tip is less than 20? Well, I know I want to test significance, so I'm going to do this. Step 1 is state the hypotheses. And again, as long as I'm making claims about a population mean, that's my template. Now, the question says, is there good evidence that the mean percentage tip is less than 20? Less than 20, right? The average of Americans. This one here has to be 20. Okay? So it's a one-sided alternative. The problem's saying less than, so I'm looking for mu being less than 20. There are your hypotheses. Step 2, your test statistic. It's a z-score. Now, if we're going to assume that the null hypothesis is true, because that's the way this works, right? Assume it's true that mu is equal to 20. The sampling distribution of X bar, right? That's where we're at. The sampling distribution of X bar, I know it's going to be normal because the population distribution of all tip percentages is normal. The problem told me that. I know it's normal. I know it's centered at 20. How do I find its standard deviation? It should be 2 over the square root of 20. Where is this coming from? It's coming from the chapter about sampling distributions. I know it's normal with mean mu, standard deviation, sigma over the square root of n. They told me sigma's 2. I know my sample size is 20. Can somebody please tell me what 2 divided by the square root of 20 is? How's that? Small. 0.447. I can do 0.45. So the standard deviation here is 0.45. So I want to calculate my test statistic, right? My z-score. I'm interested in my x bar. I want to do this. All right? Well, I know this is going to be 18.19 minus 20 over 0.45. Everybody understand where all my numbers are coming from, right? I already did the sigma over the square root of n. We did that with the sampling distribution. I know that's 0.45. I want to take my 18.19, which is my x bar that we calculated. I'd like to subtract off my mean. And I want to divide by 0.45. So what am I getting here for my z-score? I'm going to give you, obviously it's negative. Yes? My z-score is, please. Here's my question. Is that large or small? Again, the sign just tells me you're 4.02 to the left. As far as test statistics and everything go with test of significance, that's gigantic. You are more than 4 standard deviations smaller to the left of the mean. Anybody remember the 99.7% part of the rule? 3 standard deviations, 99.7% of all of them. You're further away than that. Yeah? This is huge. So the way I think about this is large. Gigantic. It's going to be so large that our little table A that we always use to find areas, hell, minus 4.02 isn't even on there. Step 3 is this. I'd like to find my p-value. All right? Now, the p-value, we have to think about what our alternative hypothesis is and where my little z-score is living. So I go here. Here is your standard normal. You know the one normal distribution mean you've been using since chapter 3? I know it's centered at 0. Where does my z-score go? My z-score is minus, what was it, 4.02? Right? Now, what does it mean the p-value is supposed to be as extreme or more extreme than your test statistic? I'm going to tell you, we got to shape one way or the other, and actually your alternative hypothesis will tell you exactly which way you need to shape by telling us what is it as extreme or more extreme. You see that? It's telling you to shape to the left. So I want the area over here. I know I'm always a red and blue guy, but since I circled that with purple, that's going to be the p-value of my test. Whatever that area is to the left of minus 4.02 being my test statistic, my z-score. That will be the p-value. Now, here's the thing. Can we look that up on takeaway? No. So what did I tell you? We don't remember. If I get a z-score less than minus 3.49, we assume that the area to the left was approximately 0, right? So the area to the right was approximately 1. So the best I can tell you here is that area right there, obviously it's not exactly 0. Approximately 0. So what I'm telling you is my p-value here, capital P, is approximately 0. Well, let me ask you this. If your p-value is approximately 0, is that large or small? I had a large test statistic, minus 4.02. I get a small p-value, approximately 0. Everybody okay so far? I haven't gotten to the punchline, right? You know, we stated the hypotheses, no calculation. Me and you calculated z-scores, these test statistics, all semester. We have found areas under the standard normal curve since chapter 3. The step 4 is okay, what's all this shit telling me? I'm going to remind you. You got a test statistic, a z, of minus 4.02. You got a p-value. Maybe I should write them both on the same page. That's a large test statistic and a small p-value. The large test statistic is telling you you're a long way out the tail. The p-value is telling you the same thing in a different way because it's checking the area in the table. The further out the tail you are, the less area, the smaller your p-value. So here's my question. Let's just make it really simple. Is the data consistent with H not being true, or is the data not consistent with H not being true is the place to start? I need some kind of general statement. Forget the problem for a second, but when I get a small p-value and a large test statistic, I need a statement that says, look, I need to do this every time, and then I'll put it in the context of your problem. What do you want to do here? Do we believe the null? Is the data consistent with H not being true? Or is the data not consistent? Not consistent with H naught. Now, obviously, that's not putting it in the context of the problem. Another thing I would say is, we got strong evidence. Against H naught. In favor That's another way for me to tell you, look, I don't believe your null hypothesis, I believe your alternative. I'm just giving you general statements here. I want to get it stuck in your head. If you see a large test statistic and a small p-value, we actually found evidence of what we were looking for. Right? So, I mean, I'm going to number these. That's one thing I can tell you. There's another thing I can tell you. Right? Okay, what else can I tell you? Let me put it in some test of significance language. We should reject the null in favor Now, here's what I'm going to tell you. None of those three answers there will ever show up as an answer on one of the final questions. Those are all general things, right? They have nothing to do with the context of the problem. I'm trying to get it stuck in your head that you don't believe the null, you believe the alternative here when your p-value is virtually 0. So then, what would I say here? Just by the way it asked me the question, we have strong evidence that the mean percentage tip is less than I'm looking at the question. That's what it asked me. Is there good evidence that the mean percentage tip is less than 20? The answer is yes. We have strong evidence that the mean percentage tip is less than 20. Why? I have a large test statistic, and I got a small p-value. Now look, that was our first test of significance from start to finish. Notice how many steps I give you? 4. State your hypothesis, calculate your test statistic z-score, find your p-value, and you got to come up with some kind of conclusion, right? What's your p-value and everything trying to tell you? Okay? Now, I don't think I'm done working problems yet, but I'd like to go back here just a little bit. Okay? And I want to look on page 401. I wanted to do a problem before we came back to this. And so it says test of significance, the 4-step process. You guys can look at that. My 4 steps and their 4 steps is not the same. My 4 steps are always the same. State the hypothesis, test statistic, p-value, conclusion. All right? I'm more interested on the bottom of page 401, and it says a 1 sample z-test for a population, mean, mu. It's 1 sample because you have an SRS here, right? All my little conditions are going to be met. It says draw an SRS of size n from a normal population that has an unknown mean mu and a known standard deviation sigma. So my thought is this. You've got to have a simple random sample of size n. You got to have a population distribution is normal. And 3, sigma is given. Those are your simple conditions. And then it says to test the null hypothesis. Now they're going to write it like this. The null hypothesis is always a statement that mu is equal to something, and they're just going to put mu subscripted with a 0, right? So there's some specific value that comes from the problem. My last problem, it was 20. Some of those other ones I worked, it was 75. Another one was 30-some thousand, right? Last week it was 0. It says to do this, calculate the 1 sample z test statistic. Look, I can't keep writing 1 sample. I want the z test statistic. It's a z-score. You're going to take your mean, whether it's given to you or whether you calculated it. We're going to subtract off the number, the mean that shows up in the null, and we're going to divide by, that's exactly what I just did to you. That's a z-score. Now, you notice here that that value shows up here that's here. We assume H0 is true. That's how it shows up. All right, so we're looking at your sampling distribution of X bar, and we're saying it's centered wherever the null hypothesis says mu is equal to. Now, the odd thing is there's 3 pictures in the bottom of this box. Here's the way I think about it. If your alternative, you know it's going to be mu naught show up in the alternative because it's always the same value in the null and the alternative. Now this is one-sided to the low side, right? So when I look at the standard normal, you're going to get your z, right? Your test statistic. That's your p-value. As small or smaller because the alternative is telling you to look to the left. Look for the area to the left. That was the problem you just did. Well, suppose the alternative wasn't one-sided to the low. Suppose the alternative was, you're going to do the exact same thing. All the z-score and everything, you're going to do exactly the same. Still the standard normal. But I'm hoping your z-score is on this side this time, because if the alternative is telling you to look to the right, I surely to God hope when we calculate our z-score that it's positive. Because if it's not, somebody's wasting our time. And where's my p-value? It's the area as large or larger than your X bar or your Z score. It's to the right. This is telling me to look to the right. This one back here is telling me to look to the left. That's how I know how to look. Which direction I'm checking the area under the standard normal. There's one other possibility. And the possibility is that the alternative is that's two-sided. Right? We didn't pick a direction. We didn't pick a side. We said different, not equal to. Now here's the thing. There's only going to ever be one z-score. There's ever going to be just one x bar. There's only going to be one test statistic. So what happens is, one of two things is going to happen. Let's say your z-score turns out to be positive and to be on that side. Then you're going to find the area in the tail as extreme or more extreme, and I'm going to call that a probability. To find your p-value here, you got to double what you found in the tail. That's the only time you got to do anything screwed up like this. And the reason you have to double it is when you started, you were going to let both tails count against your null hypothesis. Well, how do you let them both count? You double whatever you found, because there's only going to be one x bar and one z. It's going to be one way or the other. Find the area in the tail and double it. Now, I'm going to give you an OR here. Right? Still the same setup, but there's an OR. And the OR is, you get your z-score, your test statistic, and you're looking standard normal, but it just so happens your z-score is negative and you're on this side. You're going to find the area in the tail. That's a probability, and your p-value will be 2 times that. Again, why have you got to double it? Because it's a two-sided test. There's only going to be one z-score. It's going to be the left or the right. Find the area in the tail and double it. You don't have to do this crazy shit when it's a one-sided test. One side to the left, find the area to the left. One side to the right, find the area to the right. Two-sided test, your z was to the right, find that area to the right, double it. Oh no, my z was to the left, find the area and double it. Now, I think we should find ourselves another problem here. We should do 1714. Because the one about the tip percentage was one-sided to the left, I thought that was relatively straightforward. Okay? If we look at 1714 on page 404, it says, here are the 6 measurements in degrees Celsius of the melting point of a copper sample. The copper sample is supposed to have a melting point of 1084.80. Do the measurements give good evidence that the true melting point is not that value? Okay, I've got a sample of size, what is it, say 6? Okay. It says, I'm going to read this, the rest of the little information here. It says, the 6 measurements are an SRS. I'm checking the conditions on the right-hand side here. Of all results we would get if we kept measuring the melting point of a copper sample forever, the population has a normal distribution. Anybody know what I was going to look for in number 3? And sigma should be, oh, I'm happy this time. First problem me and you've done since we started these 2 chapters, it was actually, I got all 3 of them, right? You know that problem I did the first day didn't have a simple random sample. Okay? Now, it says, use information to carry out a test of significance, because that's what it says. Do the measurements give good evidence? So I'm going to do this to you again. significance? Well, the null is mu is equal to something, and the alternative is, I don't know what mu is going to be. I'm going to read the question to you again. Like I said, normally the question is about the alternative. It says, do the measurements give good evidence that the true melting point mu is not 1084.8? Not means not equal to 1084.8. If it's 1084.8, that's got to be 1084.8. That's a two-sided test. I'm going to remind you that here, and then when we get ready to calculate our p-value. Step 2. Oh, I need an X bar, don't I? Thank you. X bar is 1084.6. What did you do? You added the 6 up on the calculator, right? And you divided by 6 to get to 1084.6. And so step 2, I always like to label things for you. Here comes my test statistic. I want to remind you something. I'm looking at the sampling distribution of X bar here when we do this. I know it's normal. I know its mean is 1084.8. Remember, that's what assuming the null hypothesis does for me. It tells me where you're centered, that mu is equal to that value. And then how do I go about finding the standard deviation? I'm going to take sigma, which is 0.25, and I'm going to divide by the square root of your sample size. Just to remind you, it's normal, mu sigma over the square root of n. So would somebody tell me what 0.25 divided by the square root of 6 is? I'm assuming kind of small again. Would you get 0.100? Can I do 0.10? 0.1. I'll take 0.1. Okay. My friend says it's 0.1. I got to have that. I always like to do that up front so that when I start calculating the z-score, I don't have to think too hard about what I'm doing. I know my z-score, my test statistic looks like an X bar minus that mu naught over. Now I've already done all the work. My X bar is 1084.6, right? What's the value in the null? That's that little mu subscripted with a 0. That's 1084.8. And then we did the sigma over the square root of n to be 0.1. So my z-score here turns out to be, now I'm not expecting something that's negative or positive. It just turns out whatever it is. Is it 2 or something? Oh, no, it's way bigger than that. Oh, no, it's not. What we get? 2.00. So this is telling me my X bar is 2 standard deviations to the left, 2 z-scores to the left of the mean, yes? Now, is that large or small? What do we know about being 2 standard deviations away, right? 95% capture that, yes? So I'm not going to say, look, that's not near as large as minus 4.02, but to me that minus 2.00, that's rather large, right? So I'm expecting a rather small p-value. So I'm going to write and give you the little note here. It's not near as far out as minus 4.02. So I'm not expecting a p-value that's virtually 0. I'm actually expecting to get something this time. All right, so there's my guy. Step 3. P-value. My standard normal curve looks like this. We are centered at 0. I got a minus 2.00. I'm going to remind you something right here. I'm looking at a two-sided test here, correct? Remember, we had not equal to something. So now, what do? We run the table A, and we look up a z-score of minus 2.00. In other words, I know that I can look here and go to table A and say, I want to go to the row that's minus 2.0. The column is 0.00. You got that one, Jim? That table? No? Okay, I got it. No problem. So there's my table. It's table A. And I'm looking at minus 2.0, 0.00, and I see 0.0228. Right? 0.0228. 0.0228. I gotta keep saying it. 0.0228. So that means this right here is 0.0228. Now, if it was a one-sided test, I'd have said there was your p-value. But it's a two-sided test. So the p-value is going to be 2 times that. Remember, you had to let both tails count against you. The way you do it is whatever you find in the tail, you double it. And what do I get here? 0.0456. I'm going to give you that's rather small. Obviously not as small as the last problem, but that's rather small. Okay? Now, what's step 4? Your test statistic. Look, I'm going to give you this as conclusion. My test statistic, Z, this time was minus 2.00. My p-value on my two-sided test, P, was 0.0456. Notice, rather large test statistic, rather small p-value. Now, what we're looking at is we've got an outcome. We've got an X-bar, that 1084.6, that happens around 4% of the time when H naught is true. That's rather unlikely to happen by chance, right? See, look, with 0.0456, I always have a number in the back of my head as a p-value. And my p-value I have in the back of my head is 0.05. When I start seeing my p-values less than that, I'm going to start telling you, look, we're seeing something. We're seeing evidence against the null and in favor of the alternative. In other words, with that p-value, what I would like to do is the data are not consistent with 2. I'm not going to say strong this time. I got good evidence against H naught in favor of the alternative. I guess I can say I would like to reject H naught in favor of the alternative. The only reason I'm giving you 3 statements here, and none of the 3 are going to be what I want to end up with, is I'm hoping that one of them will click in your head and say, look, the dude had a rather small p-value. What he's trying to tell me is he doesn't believe the null hypothesis, he believes the alternative, right? In other words, my last statement here in the context of the problem would be, I got good evidence. Good evidence that the true melting point is different. Than 1084.8. Well, you wonder why I went back and looked at the book. I just copied what they said, right? Do you have good evidence? Yeah, I got good evidence that the true melting point is different than 1084.8 or is not equal to, however you want to say it. The point is, you don't believe the null, you believe the alternative because your p-value is rather small. That's two problems. The reason I did this one, I don't know how I can get this stuck in your head. That causes me to do this little odd thing here where I find the area in the tail and double it, right? That's what it causes me to do. Now, the last thing in this chapter, all right, is sometimes, look, me and you will eventually get to a problem where the test statistic is small and the p-value is large, and then the data is consistent with H not being true, and we didn't find anything, right? Both of the problems I did here today, we found something. We can answer the question is yes. Sometimes there's a fifth part. Actually, sometimes I pray for a fifth part in the problem. I didn't have to think too hard here, because, you know, I always have 0.05 in my mind. And the reason I always have 0.05 in my mind is because there's something called statistical significance. Now, this is not the first time I wrote that term up to you. I wrote that term up when we talked about randomized comparative experiments. When the effect was so large, it couldn't be due to chance. Well, I'm going to do this. I'm going to say, you know, sometimes there's like a number 5 here. And sometimes number 5 takes the place of number 4. You actually draw your conclusions in terms of statistical significance. What we're going to do is the following. We are going to compare. We compare the p-value that you calculate in step 3 with a fixed value called a significance level. The significance level is always denoted. That's the lowercase Greek letter alpha. Now, we don't get to make up the significance level. The significance level is given to you in the problem. Somebody's going to say, okay, let's compare your p-value to this significance level, and they're going to tell you what alpha is. All right? Now, one way to think about this is how much evidence against the null hypothesis we will require. Look, I mean, I know I wrote that down for you. It's okay. It's how much evidence we, against H naught we will require. In other words, how much evidence against H naught do we require before we start saying we've got evidence against H naught in favor of the alternative, right? Or we reject H naught in favor of the alternative. What it is, it's how much evidence we require before we're going to start saying is that the results are statistically significant. And you want to put it in my redneck language, it's how far out the tail do you need to be before we say, hey, your X bar is statistically significant. In other words, I'm getting ready to make how large needs to be, back in randomized comparative experience, a real thing here, right? How far out the tail do I need to be? Now, there are some standard significance levels. The standard is 0.05. That would be the 5% significance level. In other words, what we're requiring is, if this X bar would happen less than 5% of the time, you'd have to be out the tail to where there's less than 5% of the area from the tail. Sometimes people will require more evidence and say, we're requiring hells of evidence here. This is the 1% significance level. I would say somebody would try the 10% level. These are the two I think about. You know, I always think about the 5% level, and if somebody's requiring more evidence, they'll say the 1% level. So here's what we're going to do. I would like to come back here, and I want to look on page 399. And then I'm going to draw you a picture of what's going on here the best I can. All right? There's a box here. It says Statistical Significance. It says if the p-value is as small or smaller than alpha. Remember, I use big capital P as your p-value. As small or smaller. That's what it means in terms of symbols, right? Your p-value is less than or equal to your significance level. In other words, you are far enough out the tail. We say that the data are statistically significant at level alpha. In other words, you're far enough out the tail to say that your data are statistically significant. And you see this last part here? You've got to tell everybody what you compare it to. Because if I change your significance level, I can change whether you're statistically significant or not. So you always got to tell everybody at what level you are working at. The flip side of this is, if when you compare, your P is bigger than your significance level. In other words, you're not far enough out the tail. We would say the data are not consistent, are not statistically significant, statistically significant at level alpha. So you still have to go through and do all the work. You got to state the hypotheses. You got to find your test statistic, your z-score. You still got to find your p-value. But at the end, if somebody says, okay, are the data statistically significant at this level? Hell, all you're going to do is compare your p-value. If your p-value is less than or equal to that 0.05 or 0.01, hell yes, I'm statistically significant. If you're not, you're not. So for example, let's say we're doing the test of significance, right? And I've got a one-sided alternative. Now, I would hope at this point that I could write the alternative and everybody everywhere knows what the hell my null looks like. Right? The null is going to be this, right? I shouldn't have to write it, but I will. The null is, right, whatever value shows up in the alternative, the null is that you're equal to that. And let's say I have an alpha, in the problem it says, do the test at significance level alpha equals 0.05. Right? So at the 5% significance level. So when I get here, and I'm looking at my little standard normal, does everybody understand that there's somewhere here that this area here is, right? In other words, there's some value, there's some z-score under there where the area to the right of it is 0.05, right? I mean, I can find a z-score to give you any area anywhere you want under here, but there is a z-score here, right there, whatever it is, that'll have the area to its right being 0.05. Yes? So the reason I'm showing you this is this. If you show up here, in other words, your test statistic is in green, the one you calculate from your X bar during the test, right? In other words, if your test statistic shows up there, that z-score shows up anywhere there in the red, what do you know? My p-value will be less than or equal to alpha, and you will be statistically significant. That's what all this is telling me. Is how far out the tail do you need to be? Right? So if all of a sudden you calculate your test statistic, and it's any of those ones in the green, your p-value will be less than or equal to your alpha, and you'll be statistically significant. You will be far enough out the tail to be statistically significant at the 5% level. Well, what about all these guys? From here down. Let's say you get your test statistic and you're one of the ones there in blue. What happens now? Well, you're not statistically significant. Why? Because I guarantee you the p-value you get is larger than 0.05. You're not far enough out the tail. Look, I would like to explain this to you in some other way than thinking about how far out the tail you is, but that's just the way my little head works. You know, the null hypothesis tells you where you're centered. Everything I'm talking about today is how freaking far out the tail you are. The test statistic tells you this way, and the p-value tells you what's left in the tail. That's why I keep saying, the larger your test statistic, the smaller your p-value. This is just, my picture is just telling you. So why can I say something statistically significant and not? Well, if you're in the green, I guarantee you your p-value is going to be less than or equal to 0.05, right? Obviously. You'll be statistically significant. You'll be far enough out the tail. If you're in the blue, well, your p-value is going to be bigger than 0.05, and you're definitely not going to be statistically significant. Remember, I told you before, randomized comparative experiments. When the observed effect is so large that it can occur by chance, well, how large of an effect do I have to be? I have to be in the green there. I have to be out the tail far enough that the p-value of my test will be less than or equal to 0.05. Anything less than that, you're not statistically significant. Now, I'm trying to think about what else I can do to you here at this point. Please remember, we're calculating things by hand. All right? Now, one thing I would like for you to look at before Thursday, and this is not turning to me, see, my problem I have is this. The only place this shows up is in a homework problem, but I want to talk to you about it on Thursday, so I would like for you to look at it. And there's this connection of tests from confidence intervals. In other words, it turns out there's a connection between a level C confidence interval for you. Don't forget what that is, right? Level C is the success rate, right, where we're trying to estimate a population mean U, and a two-sided test at the significance level. Here's the connection. Connection is the significance level alpha turns out to be, in other words, if you got a 95% confidence interval, I want to do the two-sided test to 5%. If I got a 99% confidence interval, I want to do the significance test at the 1%, right? They add together. And where this shows up is in your textbook on page 410. I might say a little bit about it on Thursday. I would like for you to look at it. Eventually, I will say something about this, but it's on page 410. And you're going to want to take a look at problem 17.42. That's where they talk about it. The nice thing is you don't have to do any work here. It's going to be very weird that all of a sudden there's a confidence interval and a two-sided test of significance all in the same problem. But the confidence interval will tell you what conclusions you should draw about your test of significance. Now, before we go home, all right, I know I'm done, but I would like to not be done exactly yet. I've got something for you, right? And I think it could be helpful. It's kind of up to you. But under content here, I know I'm done. Under the syllabus, I have thoughts for test of significance. I'm going to make it available to everybody. And so what I've done is, there's so much freaking language I can use on you that I've taken the test of significance, and if you have a large test statistic z-score and a small p-value, I'm trying to tell you everything you can say. I've even put on here about the significance level, right? Everything I can think of. Now, these are all general statements, right? Obviously, I can't give it to you in the context of the problem, but anytime I work the problem for you, I take the context and put it in there, right? I'm going to make this available because this is everything I can think of about what the hell to say after I've got my test statistic, my p-value, and if I'm comparing to my significance level. I got so crazy that I've actually, bottom lined you here, right? Bottom line, we do not believe in all hypotheses, we believe in the alternative. That's when you have a small p-value and a large test statistic. If you want to look at it, look at it. If you want to, print it out and stick it with your book and say, I've worked the problem, now what the hell do I say? I've tried to do that for you, right? So I've tried to bring it all together, all the little pieces, everything I can think about. I've calculated what's my conclusion. All right, so I'll put that up for you. We will see you on Thursday. Be careful going into the house.